Hello there and welcome to Upper 6 Further Maths. Here we're looking at using de Moivre's theorem to prove trigonometric identities, and this is going to lead on to exercise 1D. So there are two different things that we need to be able to do with de Moivre's theorem to prove trigonometric identities. We need to go from a multiple angle to a summation of powers, like this question here, and the second thing we need to be able to do is prove a trigonometric identity from a power to a summation of multiple angles. So taking something like cos to the power of 6 theta and writing it as cos 6 theta plus dot 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 dot. So we're going to have a go at the first one first. Use de Moivre's theorem to show that cos 6 theta is equal to this expression here. So how are we going to use de Moivre's theorem? Well, what we're going to do is we're going to start by expanding cos theta plus I sine theta to the power of 6 using two different methods. The first method is going to be using de Moivre's theorem, and we know that when we've got a complex number to the power of 6, we can just multiply the arguments by 6. So the first expansion is going to be cos 6 theta plus I sine 6 theta. The second way we're going to expand this power of 6 is using the binomial expansion. Now remember, from the AS level of maths, we have a plus b to the power of 6 is this thing to do with choose functions. We do 6 choose 0, 6 choose 1, 6 choose 2, 6 choose 3, 6 choose 4, 6 choose 5, 6 choose 6, and then we go down in the powers of A while simultaneously going up in the powers of B. And that's how you can expand a bracket. So let's do that expansion. So we're going to set A here. A is going to be cos theta, and I sine theta is going to be b in this expression here. So it's going to be 6 choose 0 cos to the power of 6 theta plus 6 choose 1. We're going up in the choose here. We've gone down in the powers of cos, but up in the powers of I sine theta. It's I and sine theta that make up the component of b when you do a plus b to the power of 6. Then we've got 5 more things to go, 7 in total. So it's going to be 6 choose 4 cos to the power of 4 theta I sine theta squared plus 6 choose 3 cos 3 theta I sine theta cubed. 6 choose 4 cos squared theta I sine to the power of 4 there. 6 choose 5 cos theta, and then I sine theta to the power of 5. And the final one, 6 choose 6 I sine theta to the power of 6. Now what we're going to do now is we're going to equate just the real parts of equations 1 and 2. We'll call this equation 1 up here, this equation 2 down here, and it's just these elements here. Why are we equating just the real parts of equation 1 and 2? Because that's the cos 6 theta component. If this was a question that involved sine 6 theta equals something, then we'd take the imaginary parts of both of the expansions, but in this case it's the real parts, what cos is, so we're going to need to take just the real parts of equations 1 and 2. And how do I know which components are going to be real in this big long thing here? Well, I need to look at the coefficient of sine. It's going to be I here, so that makes it imaginary. It's going to be I squared here, and we all know that I squared simplifies to minus 1. I cubed will simplify to minus I when you expand it. I to the 4 will simplify back to I when you simplify back to 1 when you expand it, and I to the 5 will simplify to I when you expand it, and I to the 6 will expand to minus 1 when you expand it, so that's real. All 4 of these components here are real. So what we can say then is that cos 6 theta is identical to cos to the power of 6 theta minus, and now we'll do the calculation of it, 6 choose 2, that's 15, and then we've got the I squared, so that's going to be minus 1, so it's minus 15 cos 4 theta, cos to the power of 4 theta sine squared theta. Then we're going to do 6 choose 4, that's 15, I to the power of 4, that's plus 1 again, so it's plus cos squared theta, there's supposed to be a theta in there, and sine to the power of 4 theta, and then minus 6 to the power of sine to the power of 6 theta, because there's a 6 choose 6, which is just 1, and then I to the power of 6, that's a negative 1. So we've now got this expression here, and now we just need to turn it into an expression to do with causes only. So all of these sine squareds, sine to the power of 4, sine to the power of 6, are going to have to turn into cos squareds. So we can do that by doing changing sine squared into 1 minus cos squared. So it's going to be 1 minus cos squared, 1 minus cos squared, 1 minus cos squared, loads of 1 minus cos squareds appearing. Wherever there's a sine squared, 1 minus cos squared will appear. And if you expand all of that, I won't do all laboriously here, you will get 32 cos to the power of 6 theta minus 48 cos to the power of 4 theta plus 18 cos squared theta minus 1. And there we are, that's the answer to that question there. So what did we do? The method for this is expanding cos theta plus I sine theta to the power of 6. Now the second thing we need to do with a trigonometric identity using de Moivre's theorem is to prove that a power can be written as the summation of multiple angles. But the first thing we need to do with this is to remind ourselves that these little formulas here exist. These formulas here are z to the power of n plus 1 over z to the power of n equals 2 cos n theta. Z here is representing just a complex number, cos theta plus I sine theta, but when you subtract them, you get 2I sine to the n theta. So let's just prove this. Generally, this is a part A of this type of question here. So we'll take Z equals cos theta plus sine theta, and we'll raise both to the power of n, and when we do that, and when we apply de Moivre's theorem, the power of n on the outside will be moved inside to multiply by the arguments. And if we were to do that with minus n on the power, it would be minus n multiplying by the argument. Now what we're going to do now is just apply the rules of trigonometry to do with negative angles. If you've got sine of a negative angle, you can put that negative symbol to the front and bring the negative out of the bracket. And if you've got cos of a negative angle, you can just ignore the fact you've ever got a negative angle, because it will be exactly the same. It's perfectly symmetric across the y-axis. So what we'll do then is we'll ignore the negative symbol in the cos one because they're equivalent, and we'll move the negative symbol to the front for the sine one because that would now be equivalent. So what we've now got is equation 1 and equation 2. Let's first add the two together. Now when we add the two of these together, we will see that the cos n theta and cos n theta will add together to make 2 cos n theta, but the I sine n theta and the minus I sine n theta will cancel each other out when they're added together. And in fact as well, when you subtract the two, the positive coses will cancel, and the 2I sine n theta, the negative will be turned into a positive because it will be being subtracted, so you get 2I sine n theta. So these two rules here are particularly important for the next bit of work that we're going to do in the second thing that we need to be able to do in this video. In particular as well, if we just set n equal to 1 here, then we can say that z plus 1 over z, that's what it means to be a minus power, doesn't it? If you use your rules of indices, you can have z to the minus 1, that's 1 over z, is 2 cos theta, and z minus 1 over z is 2I sine theta. So these four rules here are very important for the next stage of our working. And the question we're going to have a go at now is the one down the bottom left-hand corner here. Cos to the 5 theta is equal to 1 over 16 blah 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 blah. So that's what we're going to look to prove. And the method we're going to use for this is z plus 1 over z to the power of 5, and we're going to expand that using two different methods. We've chosen to do a power of 5 because there's a power of 5 on the cos here, and we've chosen to use z plus 1 over z because it's cos, and that thing inside the brackets is equal to 2 cos theta. If it was sine to the power of 5 theta, I would be expanding z minus 1 over z to the power of 5. So the first way I'll expand this algebraically is by using de Moivre's theorem, and remembering that z plus 1 over z is equivalent to 2 cos theta. Let's now expand the bracket with the power of 5, and it will be 32 cos to the power of 5 theta. So great, we've got cos to the power of 5 theta, and it looks like we could divide potentially the 32 onto the other side at some point. Method 2 to expand this z plus 1 over z to the power 5 is, but again, by the binomial expansion. Now, I won't remind you of the binomial expansion this time, but hopefully this is familiar then. It's z to the power 5 plus 5 choose 1, z to the 4, 1 over z. The power of z is decreasing, the power of 1 over z is increasing. And the choose is going up by 1 each time. This should be a 4 here, rather. And as 5 choose 5 is 1, and 5 choose 0 is 1, so we generally don't write it. So, moving on to the next line where we simplify all of this algebra, z to the 5 on the first one, 5 choose 1 is 5, and then z to the 4 times 1 over z, that will cancel out a z, so it's z3. 5 choose 2 is 10, and z cubed times 1 over z squared is 10z. We'll carry on going down like that. Now what I'm going to do next is I'm going to now group together strategically. I'm going to group together this z to the 5 and the 1 over z to the 5 in a bracket. Then I'm going to group together the z cubeds. We've got 1z cubed and 1 over z cubed. Those two are going to be grouped together, factorising the 5 at the front. And the same for the z's and the 1 over z's with the factor of 10 at the front. I'm going to simplify it to this expression here. So, moving on with this then, I can now simplify what's in each of these brackets using the rule of z to the n plus 1 over z to the n equals 2 cos n theta. So, oh, it's down here. In fact, it's good, it's down there. So we're going to have 2 cos 5 theta plus 5 lots of 2 cos 3 theta plus 10 lots of 2 cos theta. The 5 here is the value of n, in this one here it's 3 that's the value of n, and in this one down the bottom it's 1 that's the value of n. Expand those brackets and we get this expression here. So given that we've expanded the same expression in two different ways, then these two expressions will be equivalent to each other. So the two things are equal, divide through by 32, and we get cos to the power 5 theta equals this expression here that we were looking to show. Lovely, there we are. So let's just summarize the two things that we've done there. What we've done in the first case was we expanded cos theta plus I sine to the power of 6. Reason to the power of 6 was it was cos 6 theta at the front. In the second expression, we expanded something different. It was z plus 1 over z to the power of 5 for cos, and if I was doing it with sine, I would do z minus 1 over z to the power of 5. But each time when I expand something different, the two ways I'm going to expand them is by one being de Moivre's theorem, and part B is with the binomial expansion. Then I'll set method A equal to method B, and then I'll rearrange from there. So the questions look very similar, but you can see that they are different. One has lots of powers on the other side, one has lots of multiple angles on the other side, and we need to expand something first. It's something different in each case, but both using the same method for the different ways of expanding it, de Moivre's theorem or the binomial expansion. Let's have a go at a question in action. In this question, we're looking to express sine to the power of 4 theta in this form here, and then we're looking to integrate it. So this is a way that they can use de Moivre's theorem to prove trigonometric identities and link it into integration. So what we need to do here is we need to expand z minus 1 over z to the power of 4 in two different ways. We've chosen z minus 1 over z to the power of 4 to expand because we have sine here. And sine can be written as, z minus 1 over z can be rewritten as 2i sine theta to the power of 4. And expanding the brackets, 2 to the power of 4 is 16, I to the power of 4 is 1, and sine to the power of 4 is sine to the power of 4. Let's now expand using the binomial expansion. So it's going to be z to the 4 plus 4 choose 1 z cubed. And then remember that for this part here, this whole part here is representing the b term. This first bit is the a term. So the negative symbol has to go into the minus where the 1 over z is. Same for the minus 1 over z squared. Same for the minus 1 over z cubed and minus 1 over z to the power 4. Let's now simplify all of this and then group strategically. So z to the 4's go together. Then it's going to be in both cases minus 4 times z squared and 1 over z squared. And in the last case, we just have the 6 on the end. So let's now take this and simplify what we've got. We can use the theorem of, what's the theorem again? It's going to be z to the n plus z to the minus n equals 2 cos n theta. To get 2 cos 4 theta minus 4 lots of 2 cos 2 theta plus 6. Expand the brackets on that. And now we have two expressions that are algebraically equivalent there. They're both the expansion of the same thing. And divide through by 16, we get 1 over 8 cos 4 theta minus 1 over 2 cos 2 theta plus 3 over 8. And then moving on to part B for this question, we can now integrate sine to the power 4 theta by the algebraic equivalent. And then do the integration. So remember, the way we're going to integrate is by using that wheel of differentiation in reverse. So in this case here, it's going to be cos. That's going to move back around the circle to sine. And we don't times the 4 to the front, we divide the 4 to the front when we integrate. So it's going to be 1 over 32 sine to the 4 theta, or sine of 4 theta. 2 divides to the front, and we move from cos back round to sine. Actually, minus cos back round to minus sine. So that's going to be 1 over 4. And then 3 over 8 is just a number, so that's going to be 3 over 8 theta. Substitute in your boundaries. Pi over 2 goes in first into all three places, and then 0 goes into all three places. And in that case, we're going to get 0 in the first term, 0 in the second term, 3 pi over 16 in the third term. And then when we substitute 0 in, all three terms are going to give us 0. So the answer is 3 pi over 16. So there we are. So we've got two main things to do here. So hopefully you'll have a good opportunity to practice both of those different ways of proving trigonometric identities. We'll have a go at this one here just to get us warmed up for exercise 1D. Pause the video and give this one a go. Okay, so in this case what we're going to do is we're going to expand cos theta plus I sine theta to the power of 3 in two different ways. The first way is going to be by de Moivre's theorem, so that would be cos 3 theta plus I sine 3 theta. And the second way will be by binomial expansion. So that's going to be cos to the power of 3 theta plus 3 choose 1 cos squared theta and then I sine theta to the power of 1. Then it's going to be plus 3 choose 2 cos theta and then I sine theta squared. And the last term is going to be 3 choose 3, but we know that's 1. Then it's going to be I sine theta to the power of 3. So there we are. That's the expansion by binomial expansion. Now what we're going to do here, because we want sine 3 theta, and that's sine 3 theta there, and it's got an I in front of it, we're going to set equation 1 and equation 2 equal to each other, but just the imaginary parts. So the imaginary part of 1 equal to the imaginary part of equation 2. So on the top one is going to be sine 3 theta equals, now we're just looking for imaginary things, cos cubed theta, that's not imaginary. This expression here will be imaginary, it'll be 3, because that's 3 choose 1, cos squared theta, I, but we know that's I, we know it's imaginary, so we don't need the I in it, sine theta. This bit here is not going to be imaginary because it's got I squared in it, and we know that's minus 1, so that turns it into a real number. And then the last thing is going to be minus sine to the power of 3 theta, Reason being is that this will simplify to minus I, because I squared is minus 1, there's why it's a negative there. And then we have the I there, but we don't need the I because we're just cancelling out all the I's before we start writing this equation, because we know all of this is imaginary. The only thing we need to now do is just turn this cos squared into a sine squared by rewriting it as 1 minus cos squared theta times, sorry, 1 minus, silly me, 1 minus sine squared theta, times by sine theta minus sine cubed theta. Expanding the brackets on this, I'm going to get 3 sine theta, 3 at the front, sine at the back, minus 3 sine cubed theta, minus sine cubed theta, and then simplify the last two terms, sine theta minus 4 sine cubed theta, so sine cubed theta, and that's still equal to sine 3 theta at the front there. So there we are. So that is the answer as required in the question. Okay, so there we are. So the first equation here was expanded by binomial, so by de Moivre. Second equation by binomial. Then we set the imaginary parts of the equations equal to each other. Why did I choose the imaginaries? We chose the reals for cos. We choose the imaginaries for sine. Reason for that is because I've got sine 3 theta is behind I, so it's definitely the imaginary part of this complex number, and so will these two terms here be. And then rearrange to make sure you've got the correct answer. Lovely, there we are. So that's all we're going to go through for this video then. Make sure you have plenty of practice now for exercise 1D. There's lots of different questions they can ask you, lots of different varieties. Make sure you know the 2 different main types and then how to apply in an integration question. Thanks very much for watching.